Hello, everyone, and welcome to another wonderful day of chemistry. So today we're going to be building on what we've covered so far. So last time we really built up how we could use vapor pressures to go ahead and look at liquid mixtures, as well as we've also looked at the thermodynamics of gaseous mixtures. So today we're going to really be trying to pair these together to look at the thermodynamics of liquid mixtures. So we're going to start with ideal systems and work our way to describing non-ideal. So the idea here is we can always look at the free energy of mixing any sort of species by first looking at the ideal solution. So we can figure out the chemical potential of the liquid component based on the pure chemical potential and under the ideal case, and generally the vapor pressure of each component over the pure vapor pressure for the pure system. Now, under the ideal case, we can replace this ratio of the mixed versus pure vapor pressure with the mole fraction of the component of interest. So if I've got a two chemical system under the ideal case, I can go ahead and describe the chemical potential of each component as the pure chemical potential. So this will be the standard state chemical potential I can look up in a book. Then we've got this RT correction times the natural log of the mole fraction of that component. With again, since these mole fractions will always be less than 1, the chemical potential will always be lower or more favorable for the mixture than for the pure species. So what we can do is use this information to figure out the free energy of a mixture, because the mixture will literally be just the sum of the two chemical potentials times their relative amounts. Now, if I'm looking at a impure for the mixture, we can do this by starting with the chemical potential of the pure mixture and then adding in this correction term for the relative concentrations. So this will help give me the free energy of the mixture. Now, how can I go ahead and use this to figure out how favorable mixing is? Well, I can do so by simply taking the free energy of the mixture, which we have here, and then correcting for the free energy of the pure solutions that they would have originally come from. Well, so we have our mixture component here, and then we can then go ahead and express the pure solvents, the free energy of the pure solvents, using these corrective terms. Now note when we do this, that this will go ahead and cancel out with the original reference states. Now, what this leaves behind is actually a relatively straightforward expression for the free energy mixing for for ideal systems. So as long as the intermolecular forces don't significantly change during the course of mixing, we have an equation that looks rather similar to what we saw for gases, where it's going to be based on the amount of each component and the relative mole fraction. Now, this gives us essentially four variables, though note we do have a correlation in between A and B. So we can drop a variable from the system by expressing the amount of A in terms of the total number of moles times the mole fraction of A, and then the same thing for B. So now the first term is in terms of N and T, again, defined by the system. And if we're looking at molar properties, N will just disappear. So instead, it's really defined on the temperature and the mole fraction of A, and the second term is the temperature and the mole fraction of B. And again, these mole fractions being autocorrelated. So this gives me a nice condensed way of looking at the free energy of mixing for an ideal system. We can also go ahead and use the same approach we used for gases to figure out the entropy of mixing, remembering that the entropy will more or less just be the temperature dependent term, as we again got the temperature dependent change of the Gibbs free energy, as we got this from the fundamental equation. Now, when we do this, we can take the derivative of both terms, and really what we do is we just end up eliminating both of these temperature terms, and we get the same expression we did for the ideal mixing of the mixing of two ideal gases, showing this is a relatively straightforward operation. And we can use the same approach to figure out the enthalpy of mixing for an ideal solution. Now, in this case, this will just be the Gibbs of mixing plus temperature times the entropy of mixing, at which point you may notice that the terms are rather similar, and they'll just end up canceling out. So for an ideal mixture, not too surprisingly, the enthalpy of mixing is zero, because that's the definition of an ideal mixture. For an ideal mixture, the major assumption here is the intermolecular forces didn't really change. So the intermolecular forces for the solution were the same, for the pure solutions were the same as the mixed solution. So they didn't change, so there's no change in enthalpy. So this gives us our three major variables for an ideal mixture. For an ideal mixture, enthalpy won't change. Entropy will typically increase, because again, remember those mole fractions are less than 1. And the Gibbs free energy will decrease. So all of this favors mixing. So very similar to what we saw for the gases. However, what happens if I have a non-ideal system? Now, one of our classic moves here is to incorporate all of our non-ideality into our fudge factor. In this case, our fudge factor of choice is something called the excess function, which is simply defined as how much we deviate from ideality. So the excess function can be given as that property for a given property can be given as the property of mixing minus the ideal property of mixing. So for example, let's take a look at the case of excess enthalpy. So excess enthalpy can be given as the enthalpy of mixing and then subtracting out the ideal enthalpy of mixing. Now, one of the reasons we started with this case is it's relatively simple because the ideal enthalpy of mixing is just zero. So the excess function for enthalpy is simply the enthalpy of mixing. So that makes it relatively straightforward. However, the excess functions for entropy and free energy are going to be more complicated as they actually do have ideal properties, and we have to subtract those out because they will be non-zero. However, we still need an equational form for our enthalpy of mixing. So for here, we can go ahead and start by looking at something called a regular solution. So in a regular solution, the idea here is that it's going to be non-ideal. The intermolecular forces will change, but there will be no excess entropy. This more or less means the system will mix just like if it was an ideal mixture. So there will be no clumping. It will be evenly distributed. Just thinking like it'll look like mixing two gases. Everything is perfectly well mixed. Oftentimes, our solutions are not regular, but it's a very good approximation to start with. So this means that we're going to have a very well mixed solution, but we're going to break and form intermolecular forces, and we can measure how much those intermolecular forces change based on the heat absorbed or released. So we can go ahead and express the excess enthalpy via kind of a fun little equation here. So the excess enthalpy is going to depend on, not too surprisingly, the total amount of mixture. More mixture, more enthalpy, whether it's released or absorbed. And it's also going to depend on the mole fractions of A and B. Because really, when I put these three together, that just tells me how commonly will I see will A and B see each other? The more they see each other, the more I'm going to deviate from ideality. If they see each other very little, say one of these is near 1, one of them is very near 0, then the whole thing goes to near 0, and we have very small excess enthalpy. And again, if they're near equivalent, then this will be kind of the maximum excess property. Now here, psi is going to be kind of a fun variable. So psi is going to be a measure of the strength of the AB intermolecular forces. So the stronger the intermolecular forces, the stronger the enthalpy. So again, what we'll tend to find is that if the intermolecular forces are attractive, this will be a negative psi. So if the psi is positive, this means that the intermolecular forces will be relatively repulsive. In this cases, that's going to lead to a positive enthalpy, showing again that AB bonding is unstable, unfavorable intermolecular forces. If AB tend to be attractive, well, then the psi will be negative, giving me a negative enthalpy, showing favorable intermolecular forces. So the psi is going to really tell me about the interaction strength. Now we can go ahead and graphically model our excess enthalpy using this equation. And as a result, what we tend to find is whether we have a positive or negative deviation, we're going to have the greatest impact for our excess function near these equal concentrations, which makes sense because that's when these systems will see each other the most. If it's all A, if it's all A or all B, we have no excess function because we have a pure solution. If it's close to that, it'll also still be relatively close to zero. But if I have an even mixture, that's when everyone's going to see each other the most. Now, what we find is that if the psi is positive, this will result in the most amount of energy it takes to mix. And if the psi is negative, that means we ultra favor mixing, and so we're going to be more likely to form the even mixture. Now let's take a look at those other excess functions. So again, for this regular, for our general system, we can then figure out the excess Gibbs by taking together the excess enthalpy and the excess entropy. Well, for a regular solution, we define the excess entropy of 0. That means that the Gibbs function is simple, the Gibbs of excess for a regular solution will simply be identical to the enthalpy of excess. Well, and that helps out a lot, especially because by definition, I can then figure out the Gibbs of mixing by combining together my ideal Gibbs and the excess Gibbs. So for a regular solution, that means I've got a three-term expression. We have these first two terms, which tells me how entropy will favor mixing. And then we have this third term, which will tell me what enthalpy will do. If the psi is negative, it will help pull the mixture together. If it's positive, it will disfavor that mixing. It will act as a dampening function. However, we often like expressing this instead of just as Gibbs of mixing, instead of as molar Gibbs. That way we turn it into a size-intensive property. When I do this, we can simply do it by dividing both sides by n, and what we find is now we're surely in terms of mole fractions. And again, note we also have this RT term, because again, at high temperatures, whatever we do, it's going to be magnified. And so we can go ahead and look at this Gibbs of mixing, corrected for that nRT. And when we do so, we kind of find some fun properties. So if I have a negative Gibbs of mixing, or negative psi, that means that I'm just going to tend to more favor the mixing. The real interesting thing happens when the psi is positive, because what that's going to do is it's going to go ahead and increase this curve, making it less likely for the systems to mix. Now, if the psi is just 1 or 1.5, it just kind of flattens out this bottom region. But if the psi starts getting above 2, then something kind of fun happens. So at 2, we have a very flat region, but as soon as you get above 2, now we have a bump in the middle here. Now, what that means is the most favorable mixture isn't just making an even 50-50 mixture. It's going to be making two different mixtures, one rich in A, one rich in B. And this actually becomes very important because then instead of one homogeneous solution, we're going to split into two separate mixtures. And I want you to keep this in mind later in the chapter when we take a look at phase diagrams for liquid mixtures, as this becomes really important, and we'll revisit this idea. However, next time, we're going, for the next two lectures, we're going to take a little bit of a break and take a look at colligative properties, which are really going to focus on using the thermodynamics of the solvent. Until then, take care.